of a heat curve, and then let's talk about what's happening during the process. I'm hoping that this part right here is a little bit fresher because you did it in honors chem, but we're just going to verify that we know how to calculate these different situations of phase changes. Okay, so for a heat curve, it's technically just phase changes all the way through. We're not chemically reacting anything. We're not making new substances. We're just changing the state from solid, liquid to gas. So which areas are the solid, liquid, gas? The slants or the plateaus? The slants are the solid, liquid, gas. All right, so label that for yourself. This is solid. This is liquid. And this is gas. Gas and vapor are two different things, so we do reference that as gas. So what's happening between the solid and liquid? Say again. It's melting. Okay. What's another word for melting? Starts with F. Fusion. You guys are super quiet. I can't do it. You got to help me out here. Okay. What's happening between liquid and gas? Vaporization. Good. Not really another word for that, or evaporating, but vaporization is probably the better word there. And then vice versa. If I wanted to draw this, I'm going to kind of doodle on the side over here. If I wanted to draw this in the opposite direction, I'd start where? If I want to draw a cool curve, start at gas, right? And then what's this phase change? Condensation, and then liquid, and then solidification or freezing, both work there, and then we go down to solid. Okay, so this is a heat curve on the first one. This is a cool curve. They're both cool, but it's a cooler curve. And then the axes are still heat energy. Heat energy is like generally what we use in AP chemistry. Do you guys remember what you maybe used in? No, you probably used heat energy. You maybe just said energy added in honors chem. And then what's the y-axis? Temperature. So since we're using heat in thermochemistry, we are going to generally refer to Celsius. Occasionally you could see that in Kelvin too, but generally in Celsius. So what we need to understand is that as we add heat energy, adding heat energy, adding heat energy, adding heat energy, we undergo a number of phase changes, but when is the only time temperature is changing? So on the slant, so meaning not on the plateaus, which what do the plateaus represent? Phase change, right? So phase changes do not have temperature change, okay? So during phase change, temperature does not change. And that's because what is temperature actually a measure of? So what kind of energy? Average kinetic energy, right? So the particles here in the solid, and they're condensed, they're collectively really close together, low kinetic energy. And as I continue to heat them up, what are the particles doing? Say again? Moving apart, moving a little faster. So here, the kinetic energy is increasing. It's increasing. At some point, though, it's going to get to the ultimatum of, like, do I phase change or do I keep increasing temperature? They actually will phase change by separating enough to make a liquid. So as you go here, it begins to melt. Potential energy is changing. Kinetic energy is not changing. Because obviously energy has to change, because how else is this thing going to start to spread out? No, the kinetic energy itself truly is not changing, because if the kinetic energy changed, what also would change? The temperature, right? So I definitely cannot have kinetic energy changing there, but potential energy is changing, meaning the relative positioning of the particles to each other. Yeah. To an extent, because technically it's average kinetic energy, but we do relate them because they're directly proportional, but they're not the same thing, right? Because temperature will be in Celsius, energy will be in joules, but we know the relationship there. All right, so here again, kinetic energy is increasing, and what's changing here? Potential energy, and then kinetic energy is increasing or changing. Okay, so what we can then need to determine is how much heat was applied in each of these segments of the graph. So what we know is that in terms of temperature change on solid, the liquid, and the gas slant here, since there's a temperature change, meaning there's a delta T, what equation comes to mind to calculate heat energy? Q equals MCAT, right? So on the red here, 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 I'm saying red, I can't remember. CJ's colorblind, right? So he'll color register CJ. Okay. So Q equals MCAT is what we're going to use for each of those. Does anybody maybe remember from their reading or from just general past history how to calculate heat of phase change? H of fusion. So we're definitely using H of fusion, but we have to use it with what? I heard somebody say it. Mass. Okay. So Q of a phase change is equal to mass or moles. I'm just going to put M so I can kind of go both ways. If it's given to you in mass, you can use mass. If it's given to you in moles, you can use moles. But M times delta H phase change. For this one, it's fusion because of the melting aspect here. But this one, it'll be Q is equal to M mass or moles times delta H of that, right? Vaporization. Okay. So I have to give you these values for delta H fusion, delta H vaporization. I also have already given these to you, but what are the C values for solid, liquid, gas? And let's just assume this is water. So we know the C of liquid water, specific heat capacity of liquid water, is 4.18 joules per gram degree Celsius. What was it for solid? 1.99, I think, was gas. 2.0. You guys wrote this down in your notes, and please don't guess. Just look at your notes. 2 point something. 2.1. 2.01. I'm going to find it. And 2.1. Thanks. Okay. Okie dokie. My goodness. So many notes in one. Okay. C of solid is 2.1 joules per gram degree Celsius, and C of gas is what? Or liquid vapor, water vapor. 1.99 joules per gram degree Celsius. Okay. So if I wanted to find the energy change from wherever this starts, let's just say this starts at like negative 20 degrees Celsius, and we heat water up to 150 degrees Celsius. So let's say this temperature up here is 150 degrees Celsius. What would I mathematically have to do? Qui, help me out here.
So you have to figure out how much heat is going to require the temperature. Like when you put the temperature average is 0 degrees Celsius and you find how much heat is given there.
Why are you saying 0 degrees Celsius?
Because that's when water melts.
Okay, so right here, so you're telling me to find the temperature or the heat required to go from here at negative 20 to here at 0, right? So what equation do we use here? MCAT, Q's MCAT. And then I have to find the energy it takes to go from here to here. Which equation do I use? Mass or moles times delta H. Most of the time my delta H's are in moles, so I'd be using moles, okay? So like kilojoules per mole. And then I do Q equals MCAT again, and then I do Q is equal to moles times delta H again, and then I do Q equals MCAT again. Why can't I just use Q equals MCAT for all of these slants? Because they what? Different C values. If I could, I would, but I can't. Okay, so I've got to use the different ones because of different C values. And then I have to use the different H values, delta H values there, so therefore I have to do everything as separate Q's. So how many Q's do I have? How many? 5. 1, 2, 3, 4, 5. Okay, so who gets the gist of how to problem solve? Give me a thumbs up. I mean, you don't have to make it public knowledge. You can be like right here. Okay, just kind of seeing where we are. Okay, I do want to show you one example at least. Let's do, you guys have your problem set out? I need problem set. So, question. I have a different problem set in front of me than what I gave you. Can someone read to me number 5? Is this number 5? This is it, right? Okay. So, how much heat is required to change ice, 52.9 grams of ice, at negative 15 degrees Celsius into steam at 230 degrees Celsius? Start with the person next to you. I would draw a heat curve and label the pieces just so you're clear on what you're calculating. What is it you need? 2.1 joules per gram degree Celsius. Oh. I just told you 2.1, right? It's not 2.01. Okay. I just put O up there. I'm got it then. Yeah, it's gonna be a lot of joules. Convert to kilojoules. What's up? Think about what your patients are like for easier. What'd you get? Yeah, all your kilojoules. I was not. Oh. Okay, and we're gonna say our kilojoule answers out loud and verified. Hopefully no butterfingers occurred on this one. Yep. All right. 3, 2, 1. Eyes. Thumbs up. Or close. I mean, I gotta go back and do sig figs, but full on answer here. Okay. So yes, it's tedious. Yes, it takes 5 Qs to calculate. But the thing you had to do, yes, sorry. What you do is, since you account for each Q collectively, you then sum them together to get the total heat that was required to go from A to B, which was ice to steam. So yes, you did have to convert kilojoules to joule or joules to kilojoules or vice versa, because you needed to have a uniform unit throughout before you could add. But in all, how did I get this right here? How did I get this 15? Thank you. So it goes from -15 to 0, so 0 minus a -15 is a positive 15. And then how did I get this one right here? So 0 to 100, so that's where we're melting and then eventually evaporating, or vaporization will occur. And then this last one here? 230. Yeah, going up to 230, okay? So that's why I think it's important to draw your heat curve. No matter if you really think you need it or not, you can kind of do it up in your head. I think it's important to at least identify the pieces that you need before you start to calculate. Okay? All right, so sometimes, and now this was a very elaborate one. We went from like a huge range of temperatures and we had a lot of phase changes happening. Sometimes it'll just ask you just for the heat that's required to phase change. So I just asked for, I think it's number 4, this one. How much heat will be transferred when 50.1 grams of water melts? It's just asking for the phase change one, right? So, is there a temperature change? So do I use Q equals MCAT? No, so I'm just using what? Q is equal to what? So, well, moles or mass or something, right? So the quantity times the delta H of fusion. Therefore, we can convert. What would we do with this? Convert to moles and then utilize the delta H buzz and then move on. Yeah.
So if we're giving something like besides water, we're gonna
Yeah. Yeah, it'll give it either show you in a graph or give you the melting points, freezing points. You're not expected to know anything other than water probably, and then they will give you the delta H's for those phases, those phase changes. Okay. All right. So quick break. If you won the lottery, what would you do with it? Talk first next to you. Like big lottery, like millions, trillions of dollars, quadrillions. Like you got it all. Imagine like you go to like one by invest where you were young. By the time we're like 80, you work like so much. Stop. And then have every weekend go to work. Just go to like Mexico for that. Yo, college is literally like 90% what teachers do. Yeah, no. Okay, and back to me. I want to know, like, if you have somebody that you would like to nominate to share, nominate somebody to share. Oh, you guys are. Come on now, let's go. You buy a Tesla? Well, that's like how much better?
Well, we can save on money, then we can the interest would give you more money back.
Right, but like you got millions, quadrillions, 10 billions of dollars. You buy me a Tesla too?
Yeah, sure.
Thank you. That's my that's my next car. Just saying. I'm not on the list yet, but I'll be there. Okay, so any others? Want to know some more things? Fatima, come on. Come on, Fatima.
It's a
What?
I'm like the wrong person.
Great. Good to know. James, what you got? Travel the world. Tell me, you could take us all. I mean, you got lots of money, right?
Yeah.
Okay. I would probably buy a bunch of land and have a dog park, and just all the dogs from all the towns could come and just play. And I would hire you guys as my dog hands, right? You guys could be there with me. Unless you're allergic, and we'll put a mask on you. I would pay for all of your college education as long as you came back and saw me, stuff like that. Okay. Okay. So I'm reeling you back in. Okay. You guys get this. Okay. So I have an example question up here. I want you to think of the person next to you for like a minute on problem solving process, and then I want to talk to you because I don't want you to overcomplicate it. Okay. So if 40 grams of water at 54 degrees Celsius is added to 60 grams of water at 20 degrees Celsius, what is the temperature after mixing? Assuming that no heat is lost because it's a perfect world. Nothing is lost to the calorimeter. And it gives you some other variables. Don't work too hard. Oh my God. I want to do that for one of the you don't have to. Okay, 3, 2, 1, pause. Who has a simple method not Kegels and cut? Anybody? Marcus?
You can just add them together and divide by 2 to get the average.
But see, that would be a perfect average. I would assume I have like equal amounts of water hot, water cold. I don't. Almost though, it's similar. JT?
What would you like to form a ratio of the temperatures and add those?
Maybe the temperatures, or like, what do you mean by that?
As in like use it's 40 and 60, so it's just 4 over 10 and 6 over 10.
Okay, so you're doing a weighted average, like your GPA, right? You're doing a weighted average. Okay, that is way simpler than solving for T-final for both of these, because then you got some complicated math going on. We don't have the mental capability to do that. So what I would do is let's go 40. Let's try this in our head, okay? 40 grams total of hot water that out of the total sample, which is 100 grams, right? We're gonna multiply that by, what was the temperature of hot water? 54 degrees Celsius. Okay, we're gonna add that average, or that average amount of hot water to the cold water, which was 60 grams of water over 100 grams of water at what? 20. You guys know you're presenting. Take your names down. Okay. Okay. That was what, 20? Okay. Okay. So simplify this. This, I know Marcus already told me, but go ahead. Okay, so this is 4/10, which I can work with a little bit better, plus 6/10 times 20. All right, let's make the math easy. What else can I simplify? Say again? 20. Say again? What are you saying? You're kidding. Okay, I don't know, what's 4 times 54? 216. So 216 tenths plus, what's 6 times 20? 120 tenths. Okay, so what's 216 plus 120? I'm confident you can do this. Say again. 30. Oh, yeah. 33 points, or 336, right?
Yeah.
Okay, divided by 10 is what? 33.6 degrees Celsius. Yeah.
Okay, this is a little different. It's less multiplication.
I'm ready.
Can you do 54 twice and 23 times and get 168 divided by 5?
Yeah. So you partitioned it into 5 parts.
Yeah.
So you guys are the mathematical geniuses. I'm just the chemistry person. Yeah, same thing.
Okay.
But I can multiply 54 times and add 16 on top of that. I can do that easier probably than dividing by 5. I'm not good with 5s. I'm good with 4s. Okay, but it works. It should work the same way. Okay, so or you could do it this way, which ain't nobody got time for, but it still installs to your final temperature be 33.6. It's closer to which one? In this method, this is just Q equals MCAT equals MCAT. So Q equals Q, which solving for delta T's, huh? Because it lost energy, or it's transferred energy out. So then, yeah, this is delta T, this is delta T, plugging in variable for T initials, and then collectively isolating T finals, because both of them are stopping the same thermal equilibrium temperature, and then solving for TF. Now, I would probably need a calculator for this, unless I just have because of time. Okay, which we don't. Okay, and then I have one more thought question. No, nope, we're not doing that. Okay, and enthalpy. Okay, so I like to try to make sure you're counting yourself as much math where you can. I will state that we have discussed enthalpy a little bit already. So I'm going to show you 3 different ways today to solve for enthalpy, which is delta H. But I want you guys to start me off with telling me the first way. How have we solved for enthalpy, delta H? Give me the really simplistic calculation. So delta H is just find the heat of the total reaction or solution process or whatever it may be and divide by moles, okay? So you actually already know one method. It's just we're elaborating on that and we're practicing it a little bit more more complex examples today, okay? So enthalpy is just our heat transfer. Most of the time we are talking about chemical processes when we talk about delta H, or when we talk about enthalpy. Yesterday's process was a solution process, right? We put salt, added to water, we had some thermal energy changes. Was that a chemical reaction? I mean, I could go both ways if you guys could have some evidence behind it, but what do you think? Why do you think it's physical?
Because it doesn't change. Like if it's a solid, it could be completely dissociates. But if it's like in a compound or something, the bonds of the compound and the molecules are not going to change.
So, okay, so so we had all ion things yesterday, so we were all talking about salts in general. So like sodium carbonate, and this is like one of your questions on your analysis, right, from your post lab. When you put this solid in water, right, remember we're not writing it reacting with water because that would then say, hey, we have a chemical reaction, this is hydrolysis. So we're taking this and we're making what? Sodium what? 2 sodium ions, aqueous, and a carbonate aqueous, right? So technically, yes, I have broken a chemical bond, right? I've changed the chemical composition, but I really haven't, because could I reverse this process? Yes, I could dehydrate the sample and it would crystallize right back up and I'd remake my solid sodium carbonate and be on my way. Okay, so I would say this is more physical like what we did yesterday. You could have some thoughts behind why it's chemical, but a lot of times our enthalpy is going to be for chemical reactions. Okay, I also spoke to you about how heat and delta H are related. So Q and delta H are related. They also all relate back to E, which is our internal energy change that we spoke of like a couple days ago. So there's some theory behind like when can we say Q is equal to H and when can we not? And it's all about pressure differences and volume differences. So a lot of times we'll be having constant volume situations because our solution process didn't make any gas, right? So the volume should stay constant. A lot of times our reactions are in solutions. They don't make any gases, they don't make any volume changes, so our volume will be constant. So since our volume is constant, what is work again? What's work's equation? Negative what? P delta V. If volume is constant, what is delta V? 0. Okay, so then what's work? 0. So then what's E equivalent to? Just Q, right? No work. So a lot of times our situations that we deal with are under constant volume situations. So therefore we just say, hey, constant air, or the energy change is whatever the heat did, whatever changed within heat. Under constant pressure situations, which a lot of times is what we're dealing with, because we're dealing with our coffee cup calorimeters, and we're at the atmospheric pressure, we're stuck here. We don't have any kind of pressurized room systems to change our pressure. So what we try to do is we correct enthalpy, which is delta H. We correct enthalpy to approximate Q, because most of the time under constant pressure situations, or even under any reactions we're doing, our pressure is not changing significantly, okay? So that we're saying the energy that's changing the system is equivalent to the heat energy that's changing the system. And there's a proof behind it. You guys remember doing proofs on like geometry or math too? Okay, there's a proof behind it, but just believe me, it's not worth your time. Let's just assume. Actually, I do have it at the bottom. Let us assume that enthalpy, which is delta H, approximates Q. But I won't say they're exactly equal, because what do I have to do to get to enthalpy? What do I have to do to Q? So don't forget to divide by moles, and then that's going to be our enthalpy of reaction. Thumbs up, and I can move on. So I like to give you some of the theory behind it, and then we'll do the calculation. So most of the time, we can find Q, we can find delta H. It does all relate back to the E equation, the energy change with Q and work, but many times we're not doing work in our chemistry. That's more physics. Okay. We spoke of these reaction, neutralization, combustion already, right? This is the new one. It's called delta HF or delta H naught. Do you know what I mean by naught? It's this little degree symbol. So it's this little guy right here. Okay. So when you write delta H naught or delta H degree symbol, you're speaking about a certain set of conditions. And it's very, very specific. It's like definition specific. You need to memorize this definition. I'm sorry. We don't memorize definitions a whole lot, more biology, but you do need to remember the conditions that this is speaking to. So all that stuff in blue. So the F, and maybe you know this now, but what do you think the F stands for in delta HF? It's highlighted. Formation. Okay. So standard enthalpy of formation just technically means I'm going to make 1 mole of whatever substance I want to make. Okay. So whatever substance I want to make, and so it can be an ion compound, a covalent compound, an acid, whatever. But I have to make it from its elements. So literally, whatever's on the periodic table is what I can write as to form this compound. So I'll do an example for you in a second. But when we write the naught, this just means that we're using very standardized values so that everybody in the world can use the same values and compare their data so that we can actually see if our experimental data was reliable and repeatable. So, or reproducible. Because, scientists like to reproduce values to make sure people are in line about their data and like, oh man, I discovered a new element. No, you didn't, man. It's the same as the last one. Right? So we want to have things we can compare. So notice that with thermochemistry, we're dealing with non-STP conditions, which is 25 degrees Celsius. So a lot of times you'll see the delta H like this, 298. Why are they writing 298? Because that added to make it to Kelvin would be 298, and then 1 atmosphere and 1 molar solutions. Okay. So if I were to say standard solutions or standard conditions, it means these conditions. Okay. So the standard enthalpy formation, I want you guys to write the standard enthalpy of formation for silver nitrate. Okay, so let's form silver nitrate. Form silver nitrate. Formula? Okay, AgNO3. And this is a what kind of compound? Ionic. So if it's ionic at room temperature, what likely is its state of matter? Solid, because all ionics are solid at room temperature. So if you didn't know that, you got it now. So we formed silver nitrate. And remember, we're forming 1 mole of this. So I shall not change this coefficient from 1. But what are its elements? Okay, so silver. What else? Hold on, I heard nitrate and I heard nitrogen. Which is the correct one? Nitrogen, because nitrate's not an element. It's a polyatomic ion. So how do I write nitrogen at standard conditions? N2. Okay, and then the other compound, or the other element? Oxygen diatomic. Okay, so with thermochemistry, the state of matter matters because solids have more energy than, solids have less energy than liquids and gases. I do have to write every single state of matter here. So what's the state of matter for silver? Because it's a metal, right? Okay, nitrogen. Gas, because it's a diatomic gas, and oxygen, diatomic gas. Okay, remember I told you in thermochemistry, it's the only time you can write what? Fractional coefficients, okay? Or halves, but fractional coefficients. Okay, so let's go ahead and balance this. Ready when you are? So 1 on the silver, 1/2 nitrogen, 3/2, good, 3/2 oxygen. Okay, so do use your fractional coefficients here. So this whole thing, I would then say this is the reaction for the heat. Oh, my marker is so off. This is the heat of formation of silver nitrate, and I don't know the value. I think I have it on the next slide. It's like negative 200 kilojoules or something like that. But there's going to be a number here. And that would be the energy that was either released or absorbed in the production of 1 mole of silver nitrate at standard conditions. Okie dokie? All right, we're going to do another one like this. Give me a thumbs up when I can go. Almost there. Will you remind me after? Most of us look like we're good here. Okay, perfect. So, like I said, you can use fractional coefficients. Where's my silver nitrate? I just want to know value about how much, so it's okay. All right, so we're still going to write another thermochemical equation, but I want you guys to do it for methane. Okay, so methane combusting. Go. I want 1 mole of methane. Methane is my primary target, and it's not a heat of formation one, like no delta HF. I just want you to write a thermochemical equation of methane combusting. And as my honors kids were saying yesterday, because I kind of remember math person, he was like, we love math, math's number 1. I was like, I did not teach you that. I did not. Anushka, I was like, Anushka, stop spreading lies. Math is not number 1, but it is. So things you have to do to pass your reaction prediction quiz. All right, so what are we writing for methane? CH4 combust. Okay, yields carbon dioxide and water. Okay. Balance. 2 in front of H2O. And anything else? So we have 2 plus 2 is 4. So what do I need here? 2 in front of oxygen. Okay, so it's thermochemical equation, right? So I'm going to have a delta H of combustion. At the end of this, I just don't have space, but I'm going to write a number right here at the end. Notice I'm not really adding it to the reaction, it's just kind of off to the side. And I need to figure out the states of matter, and then I can figure out the delta H combustion. So likely methane is what? Gas, because it's like cow farts, right? Gas. Oxygen is a gas, carbon dioxide is a gas, and water you could write liquid water or gaseous water. It does matter. So I'm just going to choose one for now. I'm going to put liquid, because sometimes the combustion of a really like low weight hydrocarbon doesn't create enough energy to vaporize water. It can though, so it kind of depends. Okay, so we have 5.8 grams of methane, and we know how much energy is released. So already we already know one thing about this reaction. It's saying exothermic, so heat energy is released. So I'm going to put a negative here just so I don't forget to put a negative on my reaction. And I know how much energy is released from just 5.8 grams, right? For delta H, I need kilojoules or joules per mole. So what do you guys think I'm going to have to do with this? Okay, so 5.8 grams of methane. Approximate that, guys. 16 grams of methane and like 0.4 something. Calculators. 0.3625. Okay, so I have moles of methane. 0.3625 moles of methane. Now, how do I get delta H? Q over moles. Where's Q? Okay, so we have heat released. Okay, so Q over moles. So now I'm going to take 320.0 kilojoules and divide it by the 0.3625 moles. Oh, and then I'm going to write here just a negative sign just to remember it's exothermic because it did release energy. Any takers? negative what? 0.76 kilojoules per mole. So negative 882.76 kilojoules per mole. How many sig figs do I need? Look back at the givens here. I heard 2, 3, and 4. Make a choice. It's 3 because of grams of methane, right? So grams of methane limits us to 3. So Roma's negative 883, right, kilojoules per mole. And this is speaking to moles of anything in the reaction. So it's technically like, I'm going to write that at the top now, negative 883. Squeeze it in here. Negative 883 kilojoules per mole. Scribbles. Okay. So that means that when 1 mole of methane combusts, it's releasing 883 kilojoules. When 2 moles of oxygen combust within this recipe, it creates that much energy. When 1 mole of carbon dioxide is produced in this recipe, this much energy is released. And when 2 moles of water are created through this reaction, this much energy is released. So this is per mole of anything here. It's just you can now utilize this energy in relationship to these moles or these moles as mole ratios. You can do the stoichiometry with this process. Okay, we'll get there. Can we move on? Yeah. If it mattered, but many times we're doing it with relationship to this reaction, so I wouldn't because it's usually in relationship to what's here. Okay. Figure this out. You got this. Here. I like to see what you can do before I help you. Sometimes. Check with the person next to you. Is it higher or lower than the heat convection? Is it actually higher? Okay, so it's more exothermic than the heat combustion. And we probably could have predicted that to begin with because look at the grams, right? How many grams do I have? 25 grams, which is more than the molar mass of methane, right? So I only have 1 mole of methane combusting, it's creating this much energy. So I know that I have more than 1 mole, so I should be creating more energy, right? So the number should be a larger magnitude than 883. So when you convert from grams to moles of methane, and then utilize your energy relationship for 1 mole of methane combusting, I put the negative here just to remind me that, yeah, it's the heat produced. The number here, because the way it's phrased, it is talking about a produced energy. So you don't have to put the negative at the end because it speaks to it being released. So what's this value? 1325, 85 kilojoules is released. And then I need to round that to what? 3 sig figs. 1390, 5 rounds up, right? 1390 kilojoules of energy released. Okay, you guys feeling okay still? We're still just doing Q over moles, right? It's just in reference to a real reaction now. Okay, so now, I do believe I printed this out. I might be lying. Can you guys check your notes? I tried to print more notes, like the wordy stuff. Oh, look. Oh, look. Yeah, on the back of the first page. We're just right next to those examples. Back of the first page. Killing trees every day for you guys. It's cool. All right, so there are some notes there provided for you just to help with putting pieces together in an organized fashion. So this is just a quick reminder. Anytime we have thermochemical equations, you must write the states of matter. So if you're just highlighting or circling or underlining things, states of matter matter because different states of matter have different amounts of energy. This is this enthalpy, delta H, is a function of the number of moles. So we do like to reference this as delta H is equal to kilojoules per mole whenever we write the equation or the delta H out, just to reference that, because they've changed that recently in college where they used to do some kilojoules. Now it's kilojoules per mole, so I try to make sure you're clear with that. We know our standard conditions is how do I tell you something about standard condition? The little knot thing up here, okay? And then we now know how to determine if something's endo or exo just based off the equation. So looking at this equation, I see a delta H with a negative, automatically I know it's what? It's exothermic. So if I'm holding this reaction, this is just a quick question. If I'm holding this reaction and it's reacting in here, and it's an exothermic reaction, and my hand's around it. There's my hand. Okay, 4 fingers and a thumb. There we go. I'm holding it. What am I going to feel? Okay, so I'm going to feel energy being released to me, right? If I had a thermometer in here, what would the thermometer do? It would raise, right? So if I had the opposite condition, so an endothermic process, meaning a positive delta H, and I did this, what would I feel? Why would you feel cold? Because so I heard it like 3 times. Heat's being what? Taken from you. So it's using you, right? And it's using the heat from your body. And what would the thermometer do? It would decrease. It would what? It would decrease because it's an endothermic reaction. It's one of those things that you have to think about. You can't just off the cuff answer. So just make sure you're slowing that process down. Okay. There's my silver nitrate. Boom. Negative 124. It was also negative 200 kilojoules. It was close. Let's write down the combustion. Let's do combustion. Yeah. All right. So write down the standard enthalpy change. Standard enthalpy change of combustion of ethanol. Just write a reaction. It should take you less than a minute. Standard enthalpy of combustion of ethanol. I can't write coefficients right now. All right, do we have the equation, like the predicted product? What's ethanol's formula? C, H, 5, OH. Try to keep it structural, you don't have to. Okay, what is the coefficient for carbon dioxide? Say again? It's a 1 right now, but it needs to be a 2 because I have 2 for the carbons here, and then I need a what here? 3 because I have 6 hydrogens total in the reactants, and then that's his L, by the way. 3 plus 4 is 7. What do I need here? I can't put 7 halves because I actually have an oxygen here, right? So I need what here? 3, right? So 2 times 2 is 4, plus 3 is 7, but 7 oxygens over here, 1 is already counted for, so I only need 6 here. Yes. Because ethanol is in beverages that are liquid. So ethanol, we deal with ethanol a lot, and I would give it to you because I'm not expecting you to know all the hydrocarbons, like standard states. Alcohols generally are liquid form though, like most of them. Okay. And so the combustion, heat of combustion, delta H naught is equivalent to this value here. Or the value that you can read a little bit better up there. Okay. So we're going to do a quick practice on our problem set. You guys look for enthalpy problem set. There are 9 questions on it. We're going to try to do like the first 3. So if I don't finish that today, I'll do it Monday. But I'd like to make sure you guys try to practice your homework with me before you go. I do have some notes right after this because we only still work with one way to calculate delta H. Still Q's per mole. I have 2 other ways to show you. Alright, so, and we have found our problem set. Enthalpy practice. Yes, yes? There are 9 questions. Okay. We'll do the rest of these later. Okay. So if I can try to hit 1 through 3 with you right now, the rest I'm going to leave for you for homework, but I know that you're going to need some help with them, so I want to make sure you're clear on what we're doing first. So here we go. Number 1. Can you guys write down your givens first for number 1? And just, I would start this and call it, enthalpy problem set, so you can kind of continue on this. If anybody needs paper, I've got booths of paper, so let me know. Write down your givens first. You guys can probably read the first one. Remember, it does say solution process, so I don't want you to write water as a reactant, because that would seem as if you're doing hydrolysis or salt or something for reaction. So we try to write it as a solution process. So that was for only for if you're writing heat of formation, just HF. I'll do another one I got in a second, okay? Because heat of formation is like forming 1 mole of the product based on its elements. Okay, this is a different process. Yeah. Yes. Yes. All right. So from this information, first of all, give me the equation, guys. What's the reaction? CaCl2 solid, right? Remember, states of matter. Reacts. What do you mean reacts? So yields. Okay, so yields, what are we putting on top of this? H2O, and you put H2O liquid just to verify you're talking about liquid water. And then what does it make in the solution process? 2 ions, right? Aqueous and how many? 2 chloride ions. A lot of people got that wrong when they had a question like this on the AP exam because they put the equation 2. Okay, all right, so I know that I'm going to have to put a delta H solution over here someplace. So it represents the thermochemical process. I'm just going to leave some space for that there. Okay. All right. So what's the Q for the process described? Margaret, get me started. Yeah, get me started on finding Q.
So Q equals MCAT, so the mass.
All right. So why are we using the mass of the solution?
Because it asks
Okay, so it's asking for basically the entire solution and all the energy is absorbed by the solution itself, and it also tells you to specifically assume the solution absorbs all the heat, and the specific heat of the solution is the same as that of water. Whenever it says this, thanks, Jillian. Whenever it says this right here, this is a key sign to take your mass as a total mass. Okay? Okay, CJ. We're starting homework. Let's go. All right, so Margaret said to add masses. So what was that mass? Just drop them in this. So we're just adding this up, and that's our salts, and this is our water, and then our C is what? 4.18 joules per gram degree Celsius, and the delta T is 4.9 degrees Celsius. Okay, so to find the cube solution, we're just doing Q equals MCAT, but we're summating the masses, and we're assuming the C is approximately that of water, because there's not very much salt in there. So you guys calculate Q. this just means I was summing this. Now you got me?
I got 2005.5 joules.
Okay. So joules, right? Okay, gotcha. So this is the Q of solution or water because they're one and the same, except one of them released energy, one of them absorbed energy. So I told you who absorbed energy in this question. Like I said, to assume all the energy was absorbed by the solution, like the water, the solution as a whole. And there's another key sign. What happened to the water's temperature? It what? It went up from 20.5 to 25.4. So it went up. So the temperature went up. What kind of process as a whole is this? Endo or exo? The temperature, so the thermometer read a low temperature, and as the solution process occurred, the thermometer went up. So it's exothermic. It's releasing energy. The temperature is rising because it's. So this is the part where you guys get confused. When I say release energy, you're like, oh, the energy is just gone. It's by, right? So the temperature should be lower. But it released it to something, and something had to detect the energy change. Well, what's the thing detecting our energy change? The thermometer. We don't have anything that will detect Q, like our heat changes, but we have something to detect temperature changes. So if the thermometer goes up, it is an exothermic process. If you cannot remember that, write it down, okay? So this whole process as a whole is releasing this energy. So I'm putting a negative in the front there. Okay, so the calcium chloride, which who did calcium chloride yesterday? Everybody knows now, like from those people anyway, that's an exothermic process. The thermometer went up, it got hot. Okay, so then now, what's the rest of the question say? C says, is it exo or endo? Okay, so is it exo or endo? Exo. And D says, how much heat would be absorbed by the water if 1 mole of calcium chloride were dissolved? Now, I know it's saying how much heat would be absorbed by the water, but it's referencing the solution releasing heat to the water hence is then absorbing that process, or absorbing the heat. Okay, so what is that actually asking for? Dumb that down for me. Give me like 2 words. What's it asking for? Nope. Per 1 mole is looking for delta H, right? That question is asking for delta H because it says heat released per 1 mole, so it's quantifying it per 1 mole, which means kJ or kilojoules per mole. So the question is delta H of solution. So how do I find delta H solution? Q over moles, okay? So I already have Q, it's negative 2105.55, and I'm keeping my numbers to non-sig figs just to get my final answer more accurate for now. Dividing by, I'm just going to do the math in the denominator. Yeah. I'm sorry. Did I just write kilojoules just out of the blue? I did. I'm going to stop that for a minute, and then we'll convert to kilojoules at the end. So, okay. So then my moles, I'm just going to do this in embedded math. Is it 110? What's the more math? Okay. Don't ask me. I just remembered that for some reason. Okay. So take your joules divided by your moles. So that's my embedded math there. And then we'll find our delta H. Anybody? William? Well, so what I've done mathematically is I figured out how much heat was released for this amount of solid. So that's the heat released for that amount of solid. So what I'm doing here is I'm making a new ratio by dividing by the moles so that I can then say this is the amount of heat released per 1 mole. I'm making another proportion basically. I'm solving for delta H, which is quantified per 1 mole. Okay. So let me just get a quick answer first, Cassie. Answer here, guys. It's like what? 82,000. I got 83.18 kilojoules. Did you get that too? Okay.
I got 82
When I divided, I did 110.9 when I actually did this the first time. So it's a little different, but we got about 83,000, right? Okay, negative 83. Inlo's really specific right here, but it's okay. Okay, so that's our joules per 1 mole because I've quantified the grams to equivalent to basically be 1 mole when I didn't divide. So this is the delta H of solution in kilojoules per mole. I want you guys to convert this to, I'm sorry, in joules per mole. Can you now convert this to kilojoules per mole? What is that in kilojoules per mole? Approximately negative, and how many sig figs do I need? 3 sig figs. So delta H of solution is negative 83.2 kilojoules per mole. And that is what I would write where now? At the top, at A, right? So then I would write this up here. And it didn't say standard, did it? No, so I didn't mean to put that there. Okay. Negative 83.2 kilojoules per mole. Okay, Cassie. So that's the problem. Sometimes we don't know what mass to use. So when we're finding the solution, when we're finding Q first, we do summate our masses. We have to because it specifically said assume the solution had a specific heat capacity of that of water. But water is really not doing anything. Water is just the process, just like helping the reaction occur. So we only really care about, according to our reaction, right? Notice our reaction specifies calcium chloride. That's the piece we care about to find the heat released from its own personal dissolving process or dissolution process. So that's why we specify calcium chloride here, not water. Just because it's all in reference to calcium chloride. Right, you guys do B, or 2. Do 2. I'm not doing this one. There's a video. If you can keep looking at your paper, don't look at me. I actually have to keep this board on for myself now. Yeah. This is an ion. These are in solution processes, so they're not poofing into gases. They're still in their ion form. Okay, I'm processing, pulling information and plugging in. The problem solving process takes a minute to really grasp everything. All right, good question from the peanut gallery here. So I know a lot of you guys are waiting on the rest of us, but we're finishing up our calculation real fast. Look where I wrote down the pure solution. Alright, so look on the board where I wrote down the process of Q calculation. So I know that this is a negative Q, but I know that it's endothermic. So how do I really show that to the grader? I generally will just say, okay, the Q of the reaction is equal to negative Q solution, or vice versa, Q of solution is equal to negative Q reaction. But I'm basically accounting for that negative change. So I had a negative value initially, and I calculated when I showed the process, the Q of the solution process is actually endo, so I need to have it to be a positive number. So something like that could do that for you. Or you could just say, you know, endothermic, and then show the process of changing it to positive. Don't just erase the negative and just call it a day, because you need to note that that was a change. So when you get your Q of solution, you divide by your moles of KBr. Notice I just solved this a little differently this time. Instead of dividing by the moles on the bottom, I divided by the grams on the bottom. But essentially, I'm changing to its molar mass, so I'm still getting moles in the bottom here. So tomato, it's the same process. I just want to show you guys another method to solve that for yourself. And you should get, in the end, kilojoules per mole to be about 20.2 kilojoules per mole. Okay? All right, so keep asking me questions. I'm not going to have time to teach the rest of the concepts today, so let's do 3 and 4 now, okay? Knock them out. Try start at 3. I already have a visitor. Are you So while you're problem solving and you're listening to someone here, if you feel like you have excellent study habits, and I know you all do, so that's why I can't pick. Like you're all just beautiful. But if you have excellent study habits, then I'm gonna write your name down, okay? And they're gonna ask later for S3 with an interview with you to spread the word about how to study and be a successful student.
Well, we're going to be interviewing you, but it's going to be on the S3 page.
So you could literally write down every person in our room, but just go down the hall, just go down it and just kind of just ask them. Here we go. Yeah. I have nominated you all. You do this to yourselves. I'll give you my password.
Yeah.
Okay. Okay.
Alright.
You've all been nominated. Thank you. Yeah. I can't sit. Sorry. Bye. It's not like you're getting. I mean, you're not getting an award. You're just getting recognized for your good work. All right. I have 7 minutes, precious minutes with you. Focus. What am I writing for 3? Hold on. What's the first given? Okay. Well, hold on. Mass was 4.5 grams. I have to go this way. Oh, it's burned in a bomb calorimeter. Okay, so it's a bomb calorimeter, which is going to be a little different than a coffee cup calorimeter. Oh, it's got a heat capacity. What's that? Big C. Write it like capital, right? So make sure you're not fooling yourself there. Kilojoules per degree Celsius. Okay, so I'm probably going to have to use kilojoules, William. Okay. Okay. The temperature rises. Immediately that tells you what? Okay, just to verify, we know rising temperature's increasing is exothermic, so delta T is, whatever this is, 25.2 degrees Celsius minus 21. So that's, huh? Say that again? I'm deaf. Oops. Getting old. Okay. Calculate the Q for the calorimeter and the delta H of combustion for sucrose. Okay. Ready, Freddy's? What do you want to do first? What do I want? I want to find QCal. What'd you say? Okay, so I heard a lot of people say find QCal. How are we going to find QCal? Cat. So that's our delta T. Big C delta T. Big C is what? 24.11 kilojoules per degree Celsius. And C, or delta T is, okay, so the thermometer went up in temperature. We know that it's absorbing energy, right? So maybe, I'm just going to maybe write this down for you guys. Q cal is equal to, so it's absorbing the energy, right? From what? Q of combustion, right? It's actually absorbing energy from the combustion reaction. We don't always have to write this, but we can rationalize it really easily if we do. The combustion reaction is releasing energy. The calorimeter is absorbing energy. So the Q cal itself is still going to be what? Okay, and then the Q of combustion is going to be negative. So that's why I asked them both, because you have to do them both. Okay, so go ahead, and this is what, 3.07, and what's our Q cal here? 67.9. 67.9. This is why I calculate with you. I got 74.02. Okay, 74.02 kilojoules. It's okay. Butterfingers happens. All right. So this is Q cal. So then what's Q com? So this is negative 74.02 kilojoules. Okay. So this is the answer to Q cal. How do I get Q com? I mean delta H com. So Q cal over moles or Q com over moles? Q com, so Q combustion, right? So I have to have the negative Q divided by 4.5. I got you on this. It's like 342. Okay, 342.3 joule or grams per mole of sucrose. So Q over moles, and that's going to give us a combustion. You guys tell me when you get it. negative 5,630 kilojoules per mole. You got the moles, right? Or did you put parentheses? Did that divided by this? Q divided by oops. Okay. I mean, I know it's right. It is. So I'd like to make sure you're good here. All right. So for homework, you're finishing this enthalpy problem set. So we did 3. I thought we'd get to 4. My bad. 4 through 9 for homework. Okay. Notice, and I'm gonna have to scooch these things next week. Oh, okay. But you guys are gonna not do the Hessel problem set because you don't know how to do that yet. So you didn't get there. Okay. You're doing problem set 5 through 9. Lab notebooks are due Monday. What is in your lab notebook that I haven't checked yet? Brass lab, which you should have that, right? Brass lab. What else? The gas stoichiometry, metal identification. Okay. And what lab should be finished now, basically, the one we did yesterday. So online, and I'll say online Monday, like Monday night's fine, but I'd like to grade some stuff for the weekend because, you know, that's what I do. It's fun. So, but keep listening as you kind of pack up. A lot of you guys are fantastic with your lab notebooks. I'm not talking about organization. I'm talking about completeness, okay? If it's not organized, I can usually handle it. Just make sure I can read it, please, okay? But one thing, if you have an excellent lab notebook and you're like, okay, I think I completed everything, pray with a partner and make sure that they look through. You have your procedure, you have your purpose, you have your safety, you have your data, you have all your data units shown, you have all your math, you have your conclusion, your analysis. Make somebody read your lab notebook before you turn it in. You're missing the stupid points. Like, oh, I didn't put my conclusion. Mine's 10 points. Like, I really want to give you 100 on everything, but I'm really cannot do that unless you give me quality stuff. Okay? So if she's going to look like that for you, I would go. Bye.